So, ladies and gents, now you should have drawn your graph and it looks something like this. So if this was a graphing question for the SEC, you need to make sure that your both axes are labelled, and if there are any units, they'd usually be given in your table of data that you've included those as well. I also asked you to label your peaks and your troughs and any blips with the electron configuration, final electron configuration, the final part. So helium ends in S2, neon ends in P6, as does argon. In terms of our troughs, lithium down here ends in S1, sodium ends in S1, and potassium ends in S1. Our first blip is beryllium here, and that ends in an electron configuration of S2, as does magnesium, as does calcium. Our next blip then is nitrogen here, which ends in P3, and similarly with phosphorus, it ends in P3. Now, in terms of what is the information that this graph is telling us. So firstly, this here going from helium to neon to argon is showing us that it is going down a group. So specifically it's going down group 8, but it could be any group. And it's telling us that what's happening to our ionization energy. So as you go down a group, your ionization energy is decreasing, and we'll put this into words a little bit later on. So we also then have to see what happens across a period, and I'm going to use this as my example for across a period, and we're going from lithium to neon, and as you go across a period, what's happening to my ionization energy? Well, as I go across a period, the ionization energy is increasing. So across a period, ionization energy is increasing. So if your ionization energy is increasing, it means it's harder to remove the electron. If your ionization energy is decreasing, it means it's easier to remove the electron. And we'll talk about the blips. So something is going on here that is making it slightly harder to remove electrons from nitrogen than it would be from oxygen, from beryllium than it would be from boron, and we see similar here. Magnesium, it's harder to remove from magnesium than it is from aluminium, and harder to remove from phosphorus than it is from sulfur. So the other thing that I asked you was the 4 questions that were underneath, and it was which elements are found at the peaks on your graph, and what do they have in common. So these are our peaks, helium, neon, and argon, and what they have in common is that they have full orbitals. So helium has a full s, and neon and argon have full p's, but it's significant. So there is a significance of having full orbitals when it comes to ionization energies, and whether they're high or low, and how easy it is to remove electrons. We then asked you to look at your valleys. So these are the troughs, bottom of the valleys, and these guys have in common that they all have half-filled s orbitals. So we have full orbital, or we have a half-filled, and in this case for the things in our troughs, half-filled s. If we look at question C, what do beryllium, magnesium, and calcium have in common? Well, these guys have all full s sublevel or a full s orbital. I quite like describing things in terms of orbitals, and the language you use is very important for the SEC, so pick one or the other and go with that. We then look at N and P, and what do they have in common? Well, they all have either 3 half-filled p orbitals, so again I like this one, or they have a half-full p sublevel. So you decide what you want, but you need to be able to describe what they have in common. So the half-full p orbital, and then we need to translate that into what it means for ionization energy and how easy or how difficult it would be to remove electrons from there. Now you have this information on the top of it's page 129 in my version of the notes book. So we've already done atomic radius, and we can state and we can explain atomic radius. We use literally the state and explain for explaining every other trend for things we do. So when we talk about ionization energy, we will describe, so it'll be ionization energy going across a group, or sorry, across a period, or it will be ionization energy going down a group, and we will use the blurb for atomic radius. So we'll say what happens to atomic radius and then the reasons for that increase, and we use those to explain ionization energy across a period and down a group. So if you can get that across your head, into your head sooner rather than later, you will be able to nail this. So you have this written in your book. It says state the trend in ionization energy down a group, and I've put it in the extra word describe because that could be a word that the SEC use in a question. So describe the trend in ionization energy down a group, and this is our down a group here. So we straight away, as you go down a group, our ionization energy decreases. And what this means, just in regular person speak, is it's easier to remove that outer shell electron as you go down a group. So this will be the state or explain that you're going to need, and this is just putting it into normal person kind of speak for you. So if your ionization energy is decreasing, it's easier, excuse me, to remove the outer shell electron. So then we have to be able to explain or account. So again, I've put this in, it's not in your book, but maybe you want to put it in so you recognize it from a word. So as you go down a group, the ionization energy decreases because, and now we're into the saying three things about atomic radius. So firstly, our atomic radius increases as you go down a group, and the reason for that increase is because there's an increase in the number of filled energy levels, and there is an increase in the screening effect. So this is our lesson 1 blurb, and now we're using it to explain the trend in ionization energy. So the other thing that we have to look for is now across a period. So we're going to put in describe or state the trend across a period, and this part of our graph is showing us across a period. So as you go across a period, the ionization energy increases. What does this mean for the removal of electrons? It means it's harder. It gets harder to remove the outer shell electron as you go across a period. We then link to explaining. So apologies. So it's explain or account might be the way the question asks it. So if you want to include that into your notes. So as you go across a period, the ionization energy increases, and now we're back to the three things we can say about atomic radius. Because the atomic radius decreases, and the reason for the decrease is that there's an increase in the nuclear charge, and there's no change in screening. So usually it would be these two things are the marking points, and this third one usually would not get it, but if the chief examiner wants to change her mark scheme to gain more marks or less marks for better candidates, you need to include this. You won't lose marks by including it. So that brings us to the end of today's lesson. You need to put photos of your notes into the correct page in the class notes section. There is no link in the assignment to it. You just open up OneNote, find the class notes section, find the trends page, put in the photos of your notes, and then answer the homework questions in the assignment linked class notebook page. So where the place you clicked the link for the videos, there will be a class notebook page attached to that. Your homework questions go in there, and I am on Zoom for the duration of the lesson if you have any questions. Thank you.